In the previous lecture, we saw how to construct smooth manifolds. What smooth functions are, on these manifolds are, what are smooth maps, between two such manifolds, smooth manifolds. Okay, so before we proceed, let's make a small remark. So let X be a manifold and UI contained in X a chart, a coordinate chart. Suppose V contained in UI is an open set. Let F from V to R be a map of sets. Map of sets. Then there are two definitions of smoothness. The first definition is V is contained in UI and UI is a subset of Rn, and therefore there are coordinates x1, x2 up to xn, and smooth by this definition means that f is a smooth function of the exercise. And the second definition is view V as an open subset of X and apply the definition okay, so let me not write like this. Let U j comma y1 y2 up to ym be a coordinate chart, be any coordinate chart. Then the function f restricted to v intersection uy uj from v intersection uj to r should be a smooth function of the yi's, of the yj's. So not surprisingly, both these definitions coincide. This is nice because this means that on V, the smooth functions now are the same as the smooth functions earlier. So let's see a quick proof of this. So assume that f is smooth, as in definition B, then in particular, we may take the coordinate chart ui along with the functions x1 up to xn. Then this means that f restricted to v intersection ui from v intersection ui to r is a smooth function of the exercise. But as v is contained in ui, this implies f from v to r is a smooth function of the exercise. So this part is easy. So let's see the other way around. Suppose f from v to r is a smooth function, is smooth as in the first definition. We need to check. Okay. Let u j comma y1 up to ym be any coordinate chart. Then we have a picture like this. This is my ui. V is contained inside this. This is my v. This is my uj. This is ui intersection uj. This is uji. This is uij. And here we have this portion. We have this map like this, phi ji. The shaded area corresponds to V intersection uj. And this is the shaded area here. And I have a smooth map. I have a map f from, sorry, not smooth, that's what we want to check. F from V to R. Okay, F is a smooth map in the coordinates x1 through xn. And so from this diagram, it is clear that f restricted to V intersection uj is equal to f compose phi ji restricted to V intersection uj. So since the phi ji's are smooth in the coordinates y1 through ym, and f is smooth. So what do we have? We have V intersection uj. This is phi ji. This this maps to V intersection uij, and here I have f r. So f is smooth in the coordinates x1 through xn. So this implies the composition f compose phi j I is smooth in the coordinates y1 through ym, which is what we wanted to prove. So and let's just remark that, note that if uij is non-empty, then m is equal to n by invariance of domain. So this completes the proof of the remark. Okay. So now let's begin our discussion on tangent spaces. So first we want to define germs of smooth functions. Let X be a manifold and let P in X be a point. Consider pairs F comma U where U containing P is an open set and F from U to R is smooth. So we define two pairs to be equivalent if, so I mean I have two pairs F comma U and G comma V if there is an open set W which contains P and W is contained in U intersection V such that F is equal to G on W. The equivalence classes, one easily checks that there is an equivalence relation. The equivalence classes are called germs or smooth functions at P. Okay, so now take X equal to Rn and consider the differential operator d by dxi at P. So this operator germs of smooth R-valued functions at P to real number. Defined by d by dxi at P of f is equal to df by dxi evaluated at P. So let's observe that germs of smooth R-valued functions at P is a vector space. is an R vector space. This is obvious. And d by dxi at P is a linear map, is an R linear map. And two, it satisfies the Leibniz rule. Namely, d by dxi at P of fg is equal to f of P into d by dxi at P of g plus g of P into d by dxi at P of f. So here f and g represent two germs. So this makes sense, since to apply d by dx at P, we just need that f should be defined in a small neighborhood around P. So this brings us to the definition of a tangent vector. Tangent vector at P in Rn, we are still on Rn, is a differential operator V from, so we are just taking the two properties above of smooth R valued functions at P to R, which satisfies one, V is R linear, and two, V of fg is equal to f of P times V of g plus g of P times V of f. So the second is it satisfies Leibniz rule. Thus, the d by dxi at P are examples of tangent vectors. Okay, so one easily checks that the set of tangent vectors that's denoted by PPRN is an R vector space. So we just define lambda V on F is equal to lambda times V of F, and V plus W of F is just defined to be V of F plus W of F. And we can check that lambda V and V plus W both are tangent vectors. And so this implies any linear combination at P is also a tangent vector. Okay, so let us make two observations. One, let V be a tangent vector. Then, and let lambda be an R. So we can view lambda as the constant function. Then V of lambda is equal to 0. So since V is a R linear map, it suffices to show that v of 1 is equal to 0. But this is easy since v of 1 is equal to v of 1 dot 1 is equal to v of 1 plus v of 1. And this implies v of 1 is 0. And the second condition we want to observe is that suppose f and g are germs such that at p such that f of p is equal to g of p is equal to 0, then v of fg is equal to 0. Okay, so using these two observations, we can prove the following lemma. This tells us precisely what all the tangent vectors are. Let v be in Tp_Rn, the tangent space at Rn, it's a tangent vector, then v is equal to summation I equal to 1 to n ai d by dxi at p. So the proof is an application of Taylor's theorem. So let f be a smooth function in a neighborhood of p, then we may write using Taylor's theorem f of x. So let me f of x1, x2, xn. So this is my x is equal to f of p plus summation I equal to 1 to n df by dxi at p into xi minus xi of p plus summation I less than equal to j h ij x into xi minus xi of p times xj minus xj of p. So where h ij x are smooth in a neighborhood of p. So let's denote this function by alpha and let's denote this function by beta. So note that both alpha and beta vanish at p. So now using these two observations, 1 and 2, we apply v to both sides. Applying v to both sides, we get, so v of f is equal to the v applied on the first term and v applied on the last term are 0, and also v applied on xi of p is 0. So this implies that v of f is equal to summation I equal to 1 to n df by dxi at p into v of xi. For this we can write as summation I equal to 1 to n v of xi into d by dxi at p applied on f. So this shows that v is equal to summation I equal to 1 to n v of xi into d by dxi at p. So this proves the lemma. So next we prove this proposition. So let's also prove that the d by dxi's are linearly independent, and which will prove the following proposition. The set d by dxi at p I equal to 1, 2 up to n is a basis for TPRN. So proof, we only need to show that d by dxi at p are linearly independent. So suppose there is a relation summation lambda I d by dxi at p is equal to 0, then applying both sides on xi, we get lambda I equals 0. So this proves the proposition. So thus, TPRN is an n-dimensional vector space. So now we will generalize this discussion to manifolds, and so let X be a manifold. And let P being X define a tangent vector at P to be an operator V from germs of smooth R valued functions at P to R. And as before, so such that 1, V is R linear, and 2, V satisfies Leibniz rule. The entire discussion before applies to this case. And the space of tangent vectors is denoted TPX. This is an R vector space. Vector space. And we have the following proposition. So let proposition let U x1 xn be a coordinate chart in X containing P. The space TPX as basis the set d by dxi at P I equal to 1, 2 to n. Okay. So now let's define an operation called push forward of tangent vectors. So what we want to do is suppose phi from x to y is a smooth map between smooth manifolds we are going to define d phi. This is the derivative of phi at P. There's going to be a linear map from TPX to T phi P of y as follows. D phi at P of V. So this is supposed to be a tangent vector at phi P. So what we need to do is, so if I take f, which is the germ of a smooth function at phi P, I need to say how d phi of V acts on f. So we define this as V of f compose phi. So here f is the germ of a smooth function at phi of V. So easy check. This is a linear map. Okay. So the second thing we want to check is let u x1 up to xn be a coordinate chart containing x and let v y1 up to ym be a coordinate chart containing y. So as we saw before, dpx is then the span of d by dxi at P, and d phi of P, I'm sorry, so here it should not be y, it's phi of P. Phi of P. And this is P, not x. And d phi of P y is the span of d by dyj's at phi of P. So what is the matrix? Of d phi P, d phi at P with respect to these basis. So what we need to do is we have to look at d phi p applied on d by dxi at p, and we want to know, so this is going to be j equal to 1 to m lambda j d by d yj at p, and we want to know what are the lambda i's. So what are the lambda j's? So apply both sides on yj. So then we will get that lambda j is equal to d phi at p of d by dxi at p applied on yj, and this is equal to d by dxi at p applied on yj compose phi, which is equal to d phi j by dxi. So here note that phi from u intersection phi inverse v to v looks like, in coordinates, x maps to phi 1 of x, phi 2 of x, phi m of x. Okay, and let's just make one remark that if here f is the germ of a smooth function at phi of p, and let me just add over here, this implies f compose phi is the germ of a smooth function at p, because phi is smooth. Okay, thus we get that the matrix of phi of p looks like d phi 1 by dx1 at p, d phi 2 by dx1 at p, dot dot dot, d phi m by dx1 at p, d phi 1 by dx2 at p, d phi 2 by dx2 at p, d phi m by dx2 at p, d phi 1 by dxm at p, d phi 2 by dxm at p, d phi m by dxm at p, xn, sorry. And this is a m cross n matrix. So let us observe that we remark, note that the association, the map from U to M cross N matrices given by P maps to D phi at P is a smooth map. Since each d phi j by dxi is smooth. So we will use this observation later. And one more thing we need is that chain rule can be rephrased as follows. Uh, let 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 phi from x to y be a smooth map, and let psi from y to z be a smooth map. Be smooth maps. Then d of the differential of psi compose phi at p is equal to d psi at phi of p compose d phi at p. So we can put together all the tangent vectors and form a manifold, which is what we are going to do next. So this is called the tangent bundle. So so how to do this for Rn? So let U contained in Rn be an open subset, and consider the set disjoint union P in U Tp of Rn. So this set is naturally identified with U cross Rn by sending P comma lambda 1, lambda 2 up to lambda n. Send this to the tangent vector. So we send this to the tangent vector summation lambda I d by dxi at p. So we want to do this something similar for manifolds, but that is a little bit more complicated. So suppose the manifold X is obtained by gluing UIs. UIs are contained in Rn. So define phi ij tilde from uij cross Rn to uji cross Rn by p comma v maps to phi ij p comma t phi ij at p applied to v. So this definition is naturally motivated by what phi ij does at the level of tangent spaces. Because phi ij, remember, is a smooth map, is a diffeomorphism from uij to uji. So this implies it will give rise to an isomorphism t phi ij at p from t p uij to tp t phi of p phi ij of p of uji, and this is precisely given by v maps to t phi ij at p of v. So I leave it as an exercise. Y is t phi ij, or more gently, let phi from x to y be a diffeomorphism show that d phi at p from tpx to t phi of p y is an isomorphism. This is very easy. Okay, so it is an easy check. It is easy to check that phi ij tilde satisfy the cocycle condition. So use chain rule. And I will leave that also as an exercise. And moreover, there are commutative diagrams. Uij cross Rn, phi ij tilde, uji cross Rn to uji to uij. This is the projection, and this is also the projection. The commutativity of this diagram is obvious, and we also want to check that the phi ij tilde are smooth maps. So both uij cross Rn and uji cross Rn, both these are open subsets of R to the power something, and therefore we can check what it means for a map between them to be smooth. And the point is that the coordinates of phi ij tilde are smooth functions in the coordinates x1, xn, lambda 1, lambda n. In fact, each coordinate of phi ij tilde is a polynomial in lambda i's and t phi sum a by txp. So thus So this implies gluing the ui cross Rn using phi ij tildes gives a manifold which we denote Tx, and this is the tangent bundle of x, tangent bundle of x. And the commutativity of this diagram, so let me call it star, and star implies we have a projection map from Tx to x. So we claim, that the map pi is smooth. So for this we should use the following lemma. Lemma that phi from x to y be a map of sets between two manifolds, two smooth manifolds. Suppose there is an open cover, not necessarily by coordinate charts, just an open cover wj in y such that union of wj, sorry, there's an open cover such that phi from phi inverse wj to wj are smooth maps. Then phi is smooth. So the proof is left as an exercise. And the hint is, first show that phi is smooth if and only if for every p in x there is a neighborhood v such that phi restricted to v is smooth. Okay, so using the lemma, it is clear that pi is smooth since when we restrict pi to the open subset, ui, it becomes, so it is, so then pi is exactly the projection map ui cross Rn to ui, and projections are obviously smooth. So we will end here.